Every pass through a bead mill depends on thousands of controlled collisions. The grinding medium must transmit enough energy to break agglomerates, yet remain stable while the chamber runs at speed. Composite zirconia beads are designed around that balance: ceramic density for stressing power, a hard surface for repeated contact, and rounded geometry for predictable motion. Hardness alone does not explain reliable milling. A bead that chips, flattens, or moves unevenly can change the stress field inside the chamber and introduce unwanted debris. The engineering question is therefore not simply how hard the ceramic is, but how consistently it preserves shape and transfers energy throughout the run. Zirconia and alumina can be combined in different ratios, so composite grades should not be treated as a single composition. The zirconia-rich grade in the main specification uses a zirconia yttria phase with alumina and a small silica fraction. This mixed ceramic system combines a dense zirconia-based matrix with alumina reinforcement and controlled sintering. For the zirconia-rich grade, the main technical table states a Vickers hardness above 11 gigapascals and a crush load of at least 20 kilonewtons for a 7-millimetre bead. Those values describe resistance to surface indentation and catastrophic fracture, but actual service life still depends on mill speed, slurry solids, viscosity, and chemical environment. Roundness matters because each bead repeatedly rolls, slides, and collides with neighboring media. The stated sphericity is above 96%. A more uniform spherical population supports steadier circulation and lowers the chance that sharp or irregular shapes create localized wear. In stirred milling, stress intensity rises with bead mass and relative velocity. Increasing bead density or diameter can raise the energy delivered in an individual collision, but excessive intensity may waste energy or damage sensitive particles. Selection therefore begins with the energy needed to break the feed, not with the heaviest medium available. Bead diameter also changes how often particles are stressed. Smaller media create more contact points and are useful for fine dispersion, while larger media provide stronger single impacts for coarser feed. Research on stirred mills confirms that media diameter, density, and tip speed act together rather than as isolated settings. Process stability comes from matching the ceramic to the machine and slurry. Filling level, separator gap, solids concentration, viscosity, temperature, and rotor speed all influence bead motion and wear. Even a strong ceramic medium must be validated under the actual formulation, because contamination and service life are system results, not material constants. Commercial composite grades are supplied in diameter bands rather than one universal size series. The available ranges here begin at 0.6 to 0.8 mm and extend through 9 to 12 mm, with intermediate bands for different mill scales and feed conditions. The correct diameter must remain safely above the separator opening and still be small enough to generate the required number of contacts. Feed particle size, target particle size, slurry viscosity, chamber design, and allowable contamination should be reviewed together before a non-standard diameter or composition is fixed. In coating manufacture, pigments often enter the bead mill as agglomerated particles in a liquid vehicle. Moving ceramic media compress and shear those agglomerates until the dispersion approaches the required particle size distribution. The bead must deliver enough stress without creating unstable temperature rise or excessive particle damage. Pigment dispersion influences color strength, gloss, opacity, rheology, and film uniformity. Consistent bead geometry helps maintain repeatable media motion, while the selected size and operating speed determine how quickly the dispersion develops. A stable process is measured by the finished formulation, not by milling time alone. Low wear is important because fragments from the grinding medium can alter color, filtration load, and surface quality. Composite zirconia beads are evaluated for this role through controlled wear testing under the intended formulation. A well-matched grinding medium disappears into process control, stable energy transfer, predictable dispersion, and fewer interruptions.